Rest, or representational state transfer, is probably one of the most misunderstood terms in Web API development today. Most people equate REST with anything that is easy to access over HTTP and forget about its constraints completely. The term's roots are from Roy Fielding's previously mentioned dissertation on network-based architecture. In it, Roy describes REST as an architectural style for distributed hypermedia systems. In other words, REST is not a technology, it is not a framework, and it is not a design pattern. It is a style. There is no one true way to do REST, and as a result, there are many flavors of RESTful systems. However, what is most important is that all RESTful systems manifest themselves in a set of constraints, which will be mentioned in more depth in the following section. The other common misunderstanding is that you must build a RESTful system. This is not the case. The RESTful constraints are designed to create a system that achieves a certain set of goals in particular. A system that can evolve over a long period of time and can tolerate many different clients and many different changes without breaking those clients. REST constraints. REST defines the following 6 constraints, including one optional as part of the style. Client-server. A RESTful system is designed to separate out the UI concerns from the back-end. Clients are decoupled from the server, thus allowing both to evolve independently. Stateless. For each request in a RESTful system, all of the application state is kept on the client and transferred in the request. This allows the server to receive all the information it needs to process the request without having to track each individual client. Moving statefulness from the server allows the application to easily scale. Cache data within a request must be able to be identified as cacheable. This allows client and server caches to act on behalf of the origin server and to return cached representations. Cacheability greatly reduces latency, increases user-perceived performance, and improves overall system scale, as it decreases the load on the server. Uniform interface. RESTful systems use a standardized interface for system interaction. Identification of resources. This means that the point of interaction in a RESTful system is a resource. This is the same resource that we discussed earlier. Self-descriptive messages. This means that each message contains all the information necessary for clients and servers to interact. This includes the URL, HTTP method, headers, media type, and more. Manipulation of resources through representations. As we covered previously, a resource can have one or more representations. In a RESTful system, it is through these representations that resource state is communicated. Hypermedia as the engine of application state. Previously we discussed hypermedia and the role it plays in driving the flow of the application. That model is a core component of a RESTful system. Layered system components within a RESTful system are layered and composed, with each component having a limited view of the system. This allows layers to be introduced to adapt between legacy clients and servers and enables intermediaries to provide additional services like caching, enforcing security policies, compression, and more. Code on demand. This allows clients to dynamically download code that executes on the client in order to help it interact with the system. One very popular example of this is the way client-side JavaScript executes in the browser, as it is downloaded on demand. Being able to introduce new application code improves the system's capacity to evolve and be extended. Because it reduces visibility, however, this constraint is considered optional. As you can see, building a RESTful system is not free and not necessarily easy. There have been many books written in depth on the topics just mentioned. Although making a system RESTful is not trivial, it can be worth the investment depending on the system's needs. For this reason, this book does not focus on REST but rather focuses on Evolve. Ability and techniques to achieve that when building your web APIs. Each of these techniques is a pathway toward a fully RESTful system but provides a benefit in its own right. Put another way, focus on the needs of your system and not whether you can stamp it with a REST badge or not. For more clarification on REST as a term, Kelly Sommers has a well-written post that covers this topic in more detail. To learn more about building RESTful and hypermedia-based systems, check out REST in Practice O'Reilly and Building Hypermedia APIs with HTML5 and Node O'Reilly. Conclusion. In this chapter, we learned about the origin of APIs, explored the growth of APIs in the industry, and dug into APIs themselves. Now it's time to meet ASP.NET Web API, Microsoft's answer to building APIs. In the next chapter, you'll learn about the framework, its design goals, and how to get started with it for API development. Chapter 3 ASP.NET Web API 101. It's easier to plot a course once you've seen the map. Now that we've established the context around why web APIs are important for modern networked applications, in this chapter we'll take a first look at ASP.NET Web API. ASP.NET Web API and the new HTTP programming model offer different capabilities for both building and consuming web APIs. First, we'll explore some of the core web API goals and the capabilities that support them. We'll then see how those capabilities are exposed to your code in ASP.NET Web API by looking at its programming model. What better way to examine that than by looking at the code provided by the Visual Studio Web API project template. Finally, we'll go beyond the default template code and construct our first Hello World Web API. Core scenarios. Unlike many technologies, ASP.NET Web API has a very well-documented and accessible history. Some is recorded on CodeFlex. From the beginning, the development team made the decision to be as transparent as possible so that the product could be influenced by the community of experts who would ultimately use it to build real systems. I've distilled all that history down to the core goals that ASP.NET was created to address. First-class HTTP programming, symmetric client and server programming experience, flexible support for different formats, no more coding with angle brackets, unit testability, multiple hosting options. Now, while these are key goals, they by no means represent an exhaustive list of all that the framework enables. ASP.NET Web API brings together the best of Windows Communication Foundation WCF, with its infinitely extensible architecture, client support, and flexible hosting model, and ASP.NET MVC, with its support for convention over configuration, improved testability, and advanced features such as model binding and validation. As we'll begin to explore in this chapter, the result is a framework that is approachable for getting started, and easily customizable as your needs evolve. First-class HTTP programming. When you are building modern web APIs, especially for simpler clients such as mobile devices, success of that API is often related to its expressiveness and the express Success of a web API depends on how well it uses HTTP as an application protocol. Using HTTP as an application protocol goes far beyond simply handling HTTP requests and producing HTTP responses. It means that the behavior of both the application and the underlying framework is controlled by HTTP control flow and data elements rather than by some additional data that is merely and incidentally transmitted via HTTP. For example, consider the following SOAP request used to communicate with a WCF service. Host http://localhost/greeting service.svc http://1.1 content type text/XML charset equals at 8 SOAP action hello world. Content length 154. In this example, the client issues a request to the server to obtain a friendly greeting message. As you can see, the request is being sent via HTTP. However, this is really where the association with HTTP stops. Rather than using HTTP methods sometimes called verbs to communicate the nature of the action requested of the service, the app approach shown here sends all requests using the same HTTP method post and wraps the application-specific details in both the HTTP request body and the custom SOAP session header. As you might expect, we see the same pattern repeated on the response produced by the service. http://1.1200 OK content length 984 content type text/XML charset equals at 8 date Tuesday, the 26th of April, 2011 012253 GMT. As in the case of the request message, the protocol elements used to control the API cation, that is, the way that the client and server applications understand one another, have been pulled out of the HTTP elements and placed inside the XML bodies of the request and response, respectively. In this approach, HTTP is not being used to express the application protocol, but rather as a simple transport for a different application protocol SOAP, in this case. And while this can be a good thing for scenarios where a single service needs to communicate with similar clients across lots of different protocols, it can be problematic when the need is to communicate with lots of very different clients across a single protocol. These kinds of problems are illustrated perfectly in the case of web APIs, where the diversity of not only clients, but also of the communication infrastructure between clients and services. For example, the Internet is large and constantly changing. In this world, clients and services should be optimized not for protocol independence but rather for creating a first-class experience around a common application protocol. In the case of applications that communicate via the web, that protocol is HTTP. At its core, ASP.NET Web API is built around a small set of HTTP primitive objects. The two most notable of these are HTTP request message and HTTP response message. The purpose of these objects is to provide a strongly typed view of an actual HTTP message. For example, consider the following HTTP request message. Get http://localhost 50650/API/greeting http://1.1 host localhost 50650 accept application/SN if none match 1. Assuming that this request was received by an ASP.NET Web API service, we can access and manipulate the various elements of this request using code similar to the following in a Web API controller class. var request equals this dot request. var requested URI equals request dot request URI. var requested host equals request dot headers dot host. var accept headers equals request dot headers dot accept. var conditional value equals request dot headers dot if none match. This strongly typed model provides the correct level of abstraction over HTTP/L, powering the developer to work directly with an HTTP request or response while freeing her from having to deal with lower-level issues such as raw message parsing or generation. 1. The catalog of public media types is maintained by the IANA. Symmetric client and server programming experience. One of the most appealing aspects of VastNet Web APIs